Yoichiro Nambu's 2008 Nobel Prize in Physics recognized his profound contribution to understanding the mechanism of spontaneous broken symmetry in subatomic physics, a principle that underlies many aspects of the Standard Model and beyond. His work, largely conducted in the 1960s, provided a theoretical framework for understanding how symmetries present in the fundamental laws of physics can be hidden in the observed behavior of physical systems. This essay will explore the genesis of Nambu's ideas, the core concepts of spontaneous symmetry breaking, his specific contributions, the immediate and subsequent impact of his work and its enduring legacy in modern physics. The intellectual landscape preceding Nambu's work was dominated by the challenge of understanding the strong nuclear force and the multitude of newly discovered hadrons. Quantum electrodynamics, or QED, had achieved spectacular success in explaining electromagnetic interactions, but a comparable theory for the strong force remained elusive. Early attempts to adapt QED to the strong force encountered serious difficulties, primarily because the interaction strength seemed too large for perturbation theory to be effective. Furthermore, the proliferation of hadrons, particles that interact via the strong force, suggested an underlying structure far more complex than initially anticipated. A key puzzle revolved around the concept of chiral symmetry, an approximate symmetry observed in the interactions of light quarks. Chiral symmetry implies that left-handed and right-handed quarks should behave independently. This symmetry should, in principle, lead to massless quarks and massless pions, the lightest hadrons. However, quarks possess a mass, albeit a small one, and pions, while light compared to other hadrons, are decidedly not massless. This discrepancy pointed to a breakdown of chiral symmetry. Nambu's breakthrough lay in applying the concept of superconductivity, a phenomenon well understood in condensed matter physics, to the realm of particle physics. In superconductivity, electrons near the Fermi surface form Cooper pairs due to an attractive interaction mediated by phonons, quantized vibrations of the crystal lattice. This pairing leads to a condensate of Cooper pairs, which breaks the electromagnetic gauge symmetry and results in the Meissner effect, the expulsion of magnetic fields from the superconductor. Crucially, the excitation spectrum of a superconductor contains a gap, meaning that a minimum amount of energy is required to excite electrons out of the pair. Nambu recognized a deep analogy between Cooper pairing in superconductors and the behavior of quarks in the vacuum. He postulated that the vacuum itself could be the condensate of quark-antiquark pairs. Analogous to the Cooper pair condensate in a superconductor, this quark-antiquark condensate would break chiral symmetry, giving rise to a mass gap in the quark spectrum, explaining why quarks are not observed as free particles at low energies. Furthermore, he predicted the existence of massless Goldstone bosons, particles associated with the spontaneous breaking of a continuous symmetry. In the case of chiral symmetry breaking, these Goldstone bosons were identified with the pions, which, although not perfectly massless due to the explicit breaking of chiral symmetry by the small quark masses significantly lighter than other hadrons. His seminal papers, including the 1961 work with Giovanni Gionellessinio, laid out a theoretical model exhibiting these features. This model, often referred to as the Nambu-Gionellessinio model, is a relativistic field theory with a four-fermion interaction, reminiscent of the Bardeen-Cooper-Schrieffer theory of superconductivity. The model demonstrates how a dynamical mass can arise for the fermions, even if they are initially massless, through the formation of a condensate. It also predicts the existence of a massless scalar boson, the Goldstone boson, which in the context of chiral symmetry breaking is identified with this insight into spontaneous symmetry breaking and the emergence of Goldstone bosons had a profound impact on particle physics. Peter Higgs, along with Robert Brout and Francois Inglet, extended Nambu's ideas to gauge theories, leading to the Higgs mechanism, which explains how gauge bosons, the force carriers of the weak interaction, acquire mass. The Higgs mechanism is a cornerstone of the Standard Model of particle physics, providing a crucial ingredient for its consistency and predictive power. In the Standard Model, the spontaneous breaking of electroweak symmetry, the symmetry that unifies the electromagnetic and weak forces, gives mass to the W and Z bosons, the mediators of the weak force, as well as to the quarks and leptons, the fundamental constituents. The immediate application of Nambu's work involved understanding the spectrum of hadrons. While the Nambu-Gionellessinio model provided a simplified picture, it captured essential features of chiral symmetry breaking and its consequences for hadron masses and interactions. It also inspired the development of more sophisticated models, such as the linear sigma model, which incorporated both scalar and pseudoscalar mesons and allowed for a more detailed description of pion-nucleon interactions. The subsequent use and evolution of Nambu's ideas extend far beyond the realm of strong interactions. Spontaneous symmetry breaking has become a ubiquitous concept in physics, appearing in diverse areas such as condensed matter physics, cosmology, and string theory. In condensed matter physics, it explains phenomena such as magnetism, superfluidity, and the formation of crystals. In cosmology, it plays a crucial role in models of inflation, the rapid expansion of the early universe, and in the generation of baryon symmetry, the observed imbalance between matter and antimatter. In string theory, spontaneous symmetry breaking is often invoked to explain the compactification of extra dimensions and the emergence of the standard model at low energies. The reception of Nambu's work was initially met with a mixture of excitement and skepticism. The application of condensed matter concepts to particle physics was unconventional at the time, and the Nambu-Jonah-Lassio model, while insightful, was a simplified effective theory rather than a fundamental theory derived from first principles. Some physicists questioned the validity of applying superconductivity analogies to the vacuum, arguing that the vacuum is fundamentally different from a condensed matter system. However, as experimental evidence for the existence of quarks and the validity of chiral symmetry accumulated, Nambu's ideas gained increasing acceptance. The development of quantum chromodynamics, or QCD, the fundamental theory of the strongs, provided a more rigorous theoretical foundation for chiral symmetry breaking. QCD predicts that chiral symmetry is spontaneously broken in the vacuum, leading to the formation of a quark-antiquark condensate, in agreement with Nambu's original proposal. Subsequent theoretical developments, such as the large N sub c expansion, a theoretical tool for studying QCD in the limit of a large number of color degrees of freedom, further solidified the understanding of chiral symmetry breaking and its consequences. Nambu's work directly influenced numerous physicists. As noted earlier, Peter Higgs, Robert Brout, and François Inglet built upon Nambu's ideas to develop the Higgs mechanism. Murray Gell-Mann and Maurice Levy were also greatly influenced by Nambu's insights, developing the sigma model as a phenomenological description of pion-nucleon interactions based on chiral symmetry. Steven Weinberg and Abdusalam incorporated the Higgs mechanism into their electroweak theory, which, along with QCD, forms the standard model of particle physics. The influence of Nambu's work extends to contemporary research. Effective field theories, which are based on the principle of separating physics at different energy scales, are widely used in particle physics and condensed matter physics. These theories often incorporate spontaneous symmetry breaking as a key ingredient, drawing inspiration from Nambu's pioneering work. Furthermore, the study of topological defects, such as domain walls, vortices, and monopoles, which arise in systems with spontaneously broken symmetries, is an active area of research with applications to cosmology and condensed matter physics. In conclusion, Yoichiro Nambu's work on the mechanism of spontaneous broken symmetry in subatomic physics represents a watershed moment in the history of physics. His profound insight into the analogy between superconductivity and chiral symmetry breaking revolutionized our understanding of the strong force and paved the way for the development of the standard model. The concept of spontaneous symmetry breaking has become an essential tool in many areas of physics, from condensed matter to cosmology, and its enduring legacy continues to inspire and guide research today. While theoretical physics often rewards those who uncover the fundamental building blocks of the universe, Nambu demonstrated that equally profound insights arise from understanding the hidden order and emergent phenomena that shape the world we observe. Indeed, he showed us that the vacuum, far from being empty, is rich and dynamic medium, a testament to the subtle and beautiful workings of nature. His work remains a source of intellectual inspiration, a testament to the power of theoretical physics to illuminate the deepest mysteries of the universe.